Good afternoon, everyone. My name is John Arena. I'm the product line director for Teradyne's production board test division. Joining me today is Chuck Robinson, our factory applications manager, and we're going to spend some time today talking about Industry 4.0 and the migration to automation for test, which is a topic on many of our customers' minds. This is another in our series of remote programs to try to get some topics of discussion that are current in front of our interested viewers and to foster some awareness of, in this case, Industry 4.0 and automation. We're all kind of constrained now from travel, so this is a vehicle for us to get that information out effectively. So just to start it off, Industry 4.0, the interest in greater automation, greater productivity, is really driving greater automation in every aspect of the factory. That's driven by a couple of aspects. One is improved productivity, reduced human content, and increased overall line efficiency, getting the best out of every piece of machinery. We're all aware of the current environment around COVID-19 that is accelerating the interest in automation to try to help deal with the consequences of human beings not being able to be in close proximity to each other to do work or to even be able to do parts of the manufacturing process. I think a third aspect is you're seeing on the grander national scale, the relocalization of industries to take advantage of the labor pool, to avoid tariffs, or to bring production closer to the destination where the products will be consumed. All of that blends together to drive a series of questions about automation, which we'll cover in a few moments here. Questions around test reliability, dealing with productivity and units per hour, talking about the line balance of several machines in a line, how to balance the overall flow and responsibility of each stage to get the most productivity out. How to respond with issues around product handling. Of course, the consequences of automation and test are data, product data, equipment data, how to process that information up to the manufacturing execution system into the factory enterprise. And then how does that all play together with SMEMA? So just to start, to get some vocabulary, Teradyne uses the term takt time to describe the overall interval between manufacturing steps. The takt time is broken up into two smaller pieces. One is called the processing time. That's where the value add of the process occurs. The other portion is the handling time, where a product is moved from left to right or right to left. That's really non-value added time, but it's part of the overall cycle. And the word takt is actually a German term that has made its way through the Japanese Six Sigma school of manufacturing and has now been introduced back into the East. So it's an interesting multinational flow of the concept of language. The current state of most lines that we encounter is a very advanced, fully automated inline front end where you do pick and place, solder paste, chip shoot, reflow, and inspection, followed by 3 or more islands of productivity in the back end, usually an island of functionality for process test, an island of functionality for flashing, and an island of functionality for end of line test. There may very well be more than these, such as mechanical assembly or cabling or things like that. But I want to deal only with these 3 for the moment. Each of these 3 has their own work in process pile, a collection of product coming in and a collection of product going out. That is forms a kind of a buffer. Imagine there's a buffer then at each of these 3 stages to take product in and allow that cell to work efficiently. This is the most common manufacturing flow that we see today, entering into this discussion around Industry 4.0. What Industry 4.0 means for the sake of board manufacturing are 2 key points. One is the inclusion of more of those later steps into the front end process so that they're also in line. they're automated, and that they are performed without human contact and without a buffer pile. And the second is a reduction in the amount of effort in the last stage to do final test. And this achieves a better line balance by getting more work out of the earlier equipment without impacting the takt time. And in doing so, reducing the number of individuals, the amount of equipment, the amount of fixturing in the back end. So we commonly encounter, when we talk to customers about automation, a series of questions. And I thought I would go through those one at a time and both describe what we hear and describe kind of the state of the industry now. This is not necessarily Teradyne specific. It's more test specific, but I think it's useful to explain to users kind of the state of the art in terms of automation. So the first most common instance we get is, well, today our work cell uses multiple testers. We have multiple operators, multiple fixtures. The flow is sometimes irregular. That seems very hard to automate. And there's some truth in that, in that the work cell focus is based on operators handling product and testers producing product or testing product individually at a low rate, but collectively to get to match the takt time of the line. Because of that, each of the machines' productivity isn't very visible. You're more likely to see the productivity of the cell. You're also unlikely to see the impact of the operators on the work cell productivity as they handle product, open test fixtures, perform board alignment, remove product, do barcoding, process failures. These all are part of the takt time, but it's not necessarily visible from the outside. An automated system does all of those steps automatically. The board handling is by conveyor under machine control, so it's consistent and uniform each time. The fixture handling, that is the compression and the release, is done by the handler. And again, it's done each time by automation, very rapidly, without any human involvement. The board placement and removal is done by the handler as well. So the product is stopped at exactly the right place and testing commences. The barcoding is done automatically inline as well. So there's no loss of time picking up a barcode wand or moving a product over to a barcode station. It's done completely synchronously with the rest of the process. And lastly, all of the test results are passed up to the manufacturing execution system in the enterprise, the full verbose test results, so that all of that big data set is available for the enterprise to analyze from machine to machine or factory to factory. Here's an example of that discussion. This is an actual customer of Teradyne that approached us to say their work cell was 2 testers today, non-Teradyne testers, and they, in order to improve takt time, they would need to add a 3rd. By adding automation, you can see that in, you can see that in the lower right corner. You see those 2 red circles. Those were the 2 existing testers prior to Teradyne involvement, and they would have had to add a 3rd tester to that work cell. What Teradyne was able to do was to put a single machine in place, removing the 3 testers, the blank spots you see here, removing the 3 operators, reducing the number of fixtures and area. And the most important reality is that the takt time of the original machines, which individually was about 30 seconds, times 3, was reduced to 24 seconds. So each machine would run at actually 90 seconds. You divide that by 3, you get to a 30-second net takt time for the work cell. We were able to achieve that with a single machine in about 24 seconds. This is a snippet of a much longer video, the link to which on YouTube will provide to viewers of this webinar after this event concludes. But it's a fascinating case study, and the video is not done by Teradyne. It's been done by the customer to present their Industry 4.0 forward-looking perspective. This was a success story to them. So we're proud to repeat that here as well. The next comment we hear is, okay, I understand the work cell and the productivity, but we have a lot of manual steps we do today around repair tickets, repair generation, process flow around repair. So in the manual system, the tester completes the test. There's some local data storage of failing data. A printer at that stage may issue a paper ticket, which is put on top of the product. The product is then sent to a next stage or a repair station. And at that stage, the operator picks the product up, picks the ticket up. They may barcode the board to get more results back. But it's a very manually intensive system, and it's very much one way. The data comes from the tester and goes to a destination, but there's not a lot of exchange of data between test and repair station. In automation, that repair data is logged locally and transferred also to the repair station, as well as the enterprise. The barcode is used to recover the repair data, so there's no paper ticket at all involved. By barcoding the board, I can see what stage it's proceeded through, what the repair data conclusions were. All of that data log information is recorded based on barcode, so there's a permanent record of the test results, be they pass or fail. And that can be retrieved anywhere in the factory or anywhere in the world by a manufacturer. So you can start to look at trends, you can start to look at patterns in the factory and in by operator or by work shift, et cetera. So most of the paper steps are eliminated in favor of data collection, and the process flow of work eliminates the need for hand touch. This is all done by automation. Products to be repaired are loaded into magazines, which are then, or by shuttles, which are then sent off to a repair station. So a very different, much more efficient approach with automation. What I thought I'd do now is there's another series of topics around testability and how automation addresses testability. I wanted to turn this over now to my colleague, Chuck Robinson, to take us through the next couple of slides on this topic. Chuck?
Okay. Yes, thanks, John. So one of the things we see frequently in a manual system is people are concerned about giving up their operators. And the reason being is that very often the operator is a very critical person in that step, because maybe their systems are older, and so they're maybe not as reliable, or maybe the test program can sometimes be unstable, or the fixture is kind of balky. And so that operator actually is critical in, maybe retesting a board or interpreting results or monkeying with the fixture to get it to seal or something like that. And so, those problems don't have to exist, but sometimes they just do naturally, or maybe there's no time to fix some of those problems, right? So, but they shouldn't be nervous about eliminating the operator, because when you go into an automated system, first off, it's going to be a newer system, right? We have features like auto calibration, where your instruments are calibrated either on a time basis or on a temperature basis. If you exceed a temperature range, then they'll be auto calibrated. We also have many tools from both development and debug through validation and release to the factory floor, and then on into ongoing monitoring of your process that ensure that your program is both stable and repeatable and is meeting your metrics for CP and CPK, such that you don't have to tolerate, or you shouldn't tolerate, any false failures or any retest issues. Then you have coverage reports to ensure that you're getting full coverage. As John mentioned, there's data logging that goes on. There's data that's both stored on the system for later analysis, and also, again, refining your process over time. And we also have tools for optimizing your throughput, again, for meeting that takt time. So in addition to removing the handling, you also can optimize your program to run at the most optimal level. So here's an example of some of these software tools. On the left, you're seeing our real-time debug tool, where as you're debugging individual components, and you're often looking at your more troublesome components, you can also get in the right, you see there a graphical display of the measured values during debug, and statistics such as CP, CPK, standard deviation. So even before you're finished your development, you're able to begin to monitor the stability and repeatability of your tests. And then on the right-hand side, you see a display that's created from your logging data. So as you're producing boards and gathering data, you can load this data into a tool called data display, and this would allow you to, display on a timeline your component CP, CPK, standard deviation, and then when needed, you can drill down into the individual component measurements and see where they're distributed on a histogram. So again, that's very useful for both development, release to production, and then monitoring over time.
Thank you, Chuck. One of the other comments we receive in talking to customers is the matter of complexity. The product is too complicated to do automated tests, Teradyne. And that may have been true as recently as 5 years ago, but most recently, systems that have very high test point count are furnished into the field and operating successfully. Our current capability extends to up to 6,400 hybrid test points, the ability to put dual site or dual testers in one automated handler for panelized product. And that whole solution then maintains the productivity of the system. Another comment we get is regarding test fixtures. These newer products are fully capable of complex and large geometry products such as servers, switches, datacom, telecom type large geometry boards that can be up to 400 to 500 millimeters in dimension. So these are today routinely tested on automation. With regard to fixtures, remember in a manual fixture case, either vacuum or pneumatic cylinders are used to create that downward pressure, and that capability has to be built into each fixture. The fixture has to be built to be robust to deal with that pressure. And it opens like a clam with a hinge-based solution. So you've got cables in the middle. So you have mechanical repetition. You have potential for fatigue of cables, et cetera. An automated system changes the use paradigm. The fixture is split into two parts, each which we call a jig. Each jig is loaded into the handler, and they're brought together for the purposes of testing by the pressure of the machine. So each fixture can be made less robust. There's no need to build the compression capability into the fixture, so you're not spending that energy and money in each fixture to do that. And there's examples of literally hundreds of these fixtures running today on Teradyne systems successfully in a lights out environment. So in terms of reliability or complexity, the automated fixture solution is a proven, reliable, and robust capability for deployment. Here are a couple of examples of test fixtures. And Chuck, I might ask you to jump in here and talk through what we're looking at on these two.
Yeah, sure. On the left-hand side, we're seeing quite a complex automated fixture. This is testing an LED taillight array for an automotive solution. So what you're seeing inside the fixture here is literally dozens of LED light pipes that then go to LED test modules. There's some additional support electronics in there to communicate with the product and do some in-system programming on the product. And we're also doing a full in-circuit test. We're powering up the board and doing a number of other standard things. But here is quite a complicated functional level test that's being done, and all that supporting electronics can be fit inside the fixture in a kind of a nice, neat way. And on the right-hand side, we see another automotive solution. This is a 16-up panel of small automotive controllers. This is a custom controller. And in this instance, we're doing standard in-circuit test as well as some programming, in-system programming of the custom microcontroller using our tester hardware, and also some calibration data is being loaded as well. And one of the features to point out here is that you can make out here that the test probes are not all the same height. There's some longer than the others. And so one of the built-in benefits of the automated system is that doing dual height testing is quite easy. So in this case, we're doing a dual height. We're removing the in-circuit probes and leaving just the power and functional test probes during the in-system programming portion. And any kind of custom level programming that's required for the fixture is built into the database on the handler, such that when you load that program, the profile of the fixture is loaded automatically as well. So it's kind of follows the fixture along. Anything special with the fixture is kind of built in automatically. So it's very convenient.
Thanks, Chuck.
You're welcome.
There are a couple of unique aspects of automation that customers and users need to anticipate. The first is that the product's moving from left to right or right to left. That means you've got to anticipate how do you move that product? How does it behave while under movement? Is it a heavy product? Is it a light product? In the case of the Teradyne solution, the parameters I'm about to talk to are stored. Those are parameters such as the speed at which the product should enter the handler. The handler is under control of the conveyor speed. So to slow down heavy products gently and to properly handle the difference between light products and heavy products, we store that conveyor speed and a slowdown profile so that we know in advance that right acceleration and deceleration is appropriate for that size product, and it's different for every board. A second issue is the outline of the board, what we call the profile. If the outline is rectangular, the product will stop based on the leading edge of that rectangular board. If the product has a non-rectangular profile, the stop performance of the machine needs to be adjusted to anticipate that the edge that's detected may not be the leading edge, but might be a portion of some other part of the product. And again, these parameters, once recorded, once programmed, are stored in the machine and coded by fixture ID so that once set, they don't have to be adjusted again. Another aspect of automation programming that's a little different than manual is the concept of multi-threading. In order to improve takt time, Teradyne and others make use of multi-threading programs. What does that mean? Well, while we're testing board B, we're in parallel doing some pre-processing tests on the board that will enter next. So while we're testing board B, we're reading the barcode of board A. We're sending that data up to the manufacturing execution system and pulling back data such as proceed, or here's your MAC address, or here's some calibration data, so that those steps are no longer done in the next step. They're already done and the data is waiting. Likewise, after board B is tested, we're doing what's called post-process testing on board C. Those are steps like transmitting the data to the enterprise system, waiting for the results back from the enterprise system in terms of what direction we should get in terms of sending that board to the pass line or the fail line, or to hold it for review, etc. Because these steps are done in parallel, the overall takt time is reduced versus that if they were done in series. And this is one method that automation can improve overall takt time of test that manual testing really can't do, because they're typically done by one operator in a serial form. So again, this is one method by which automation is much faster in test than are human beings. Again, this is another in our series of our online seminars. We're doing this in an effort to compensate for our inability to visit you folks. So we're very glad that you're able to join us today. I want to remind you that the link to that video of that transition from manual to automatic test will be available after this session. And I'd invite you to send me questions directly. My email is shown here. We don't get out as much as we used to with the global pandemic, and there's an opportunity to answer a question or two. We look forward to the opportunity. So again, thank you very much. Look forward to seeing you again on another LinkedIn Live session.